Hi, my name is Noah Boyd, and in this video, I would like to share a project I did a few years ago when I was in high school. This Python program rotates a 3D wireframe cube and then projects it onto the screen. And I like to show how I did this. And I have this custom Windows terminal script to help show the code. And I'll go ahead and erase everything. Uh, First, you start with your imports. We're going to import sys to control exiting our program, and we'll use Pygame and Pygame submodule gfxdraw to animate the wireframe cube, and our math module for the rotation that we will later show how it's implemented. Next, we're going to define a few constants. So we're going to define screen width and screen height. It controls the size of the screen produced, and we'll also define our background color, which is just white. And I clicked too many earlier, but we also have a draw background function. So if you wanted to change this, you could change it to a gradient, but all I did was a plain Jane white background. And then we're gonna see our function to handle key inputs. And the only key input that this handles is the quit function, quit event, which is when you click the X on the window that Pygame produces. When you click that, this function will then return false, and we'll use that as a signal later to terminate the program. Now we're getting into the rotation matrices that I hinted at earlier. Got the math for this from Wikipedia's page on rotation matrices and just implemented it in Python. So they each take, and I have a different one for rotating on the x-axis, rotating on the y-axis, and then also the z-axis. But they all take the same format of input. They take an xyz variable, which is a tuple, which is just a list that is immutable. Takes a tuple of the x, the y, and the z values of a coordinate, which will be each of the 8 vertexes of our wireframe cube. And then it takes the desired angle to rotate this coordinate. It applies the rotation matrix by converting the angle to radians, and then it will produce a new tuple and return that, and it will become the new coordinate. Now we're getting into the, I guess you would call this the business logic of the program, even though we have some math functions here. But in our main function, we're going to first initialize Pygame. We'll let our mouse still be seen, and we're going to initialize clock variable so that we can control the frame rate of our animation. And we'll go ahead and throw up our screen. And now we're going to build our cube. We'll first build the vertices, and then we will build the edges. So my approach to this was to start with a square, and I defined each vertex of the square, starting with the first quadrant, 1, 1, and then going counterclockwise through the quadrants, the quadrants on the coordinate plane, the xy coordinate plane, through quadrant 2, 3, and 4. And then I defined a scalar value, and I use this to scale up each of the values of every one of our vertexes, simultaneously while building the cube list of our vertexes. Then, keeping in mind that I had defined the square face vertexes in a counterclockwise fashion, and then first defined in our cube the back side and then the front side, I used a few more list comprehensions to define the edges. So this first one will define the front edges, where it takes the first vertex and then connects it to the next one since they happen to be in order. And when it gets to the last one, when it adds one, it wants to reference back to the first vertex, which is vertex 0. So that's why I did modulo 4 here. And then it's similar for the backside. We're just going to add 4 because the backside and the front side are offset by 4 in the list. And you wouldn't want to add this inside here because that affects the modulo. And then we have to connect our two faces. So we're going to connect one vertex to the vertex that is displaced by 4 places in the list, but it corresponds to the one that is behind it when looking at it. And then I just printed those lists out to make sure I got the coordinates and the edge connections right. And now we are going to get into manipulating our angle, the angle of the wireframe cube. And vertex size is just the size of the point that iGame is going to draw for a vertex. Similarly, I defined the wire color as black. And this is our main loop here. First, we're going to get a frame from the clock. And then this is our handle keys function. So if it were false, it would break the loop and exit the loop, and we'll be able to exit our program. But if it returns true, that means keep going. So, and then we will first draw our background. And now we're going to manipulate our coordinates, the vertexes of our wireframe cube. So we're going to apply each of these rotate functions to each of the vertexes with map, applying our angle to change. So the approach that this is taking, that I took, it first takes the original cube and is going to rotate it by the current angle. So it's not adjusting it from the last position. It's taking the adjusted angle and applying that to the original cube. So it takes the original cube, rotates it, and then it rotates the rotated by the next I see I made a mistake here. One of these should be Y. All right. And now we have to project our 3D object into 2D. So the way we're going to do that is we're going to use perspective. We're going to consider the camera being 300 units away from the origin. So imagine the origin is in front of us 300 units, and we will scale that down by a factor of 200. It makes it fit well on the screen. But if this ratio were to be 0, we're going to end up dividing by it. So we want to just set it to 1 at that point to avoid a divide by 0 error. And now we will, for an individual point, we will project it on here. So our xy is going to be offset from the screen width and the screen height by the value of x and y on the coordinate plane, and then taking our distance away from the camera, the z value we calculated earlier, we'll divide it so that things farther away appear smaller. And if our z value is closer, it'd be dividing by less, so it would appear larger. It'd be more stretched out on our screen. And using a anti-aliased circle, what that does is it draws a circle, and instead of just filling in the pixels to the color reset, which is black, it will blend the edges around the room between black color at the vertex and the white background, so that it's a nice smooth transition and it looks more like a circle. It's easier on the eyes. And however, the anti-alias circle function, it only produces the perimeter of the vertex. So it just looks like a circle. So we're going to fill that circle as well. And we will append it to our list of projected XY. And the reason why we're appending it is so we can use it for drawing our edges. So for every edge, we're going to get the points that it's referencing to. And we will simply draw a line from point to point. And we will use screen.blit to redraw the surface. So everything you did before, it would not necessarily render to the screen immediately, but with screen.blit, it does. It pushes that change to the screen. Or maybe not, maybe I'm wrong. One of these does that. I guess I forgot what screen.blit does. My bad. But then after that, we're going to update our angle. So, like I was talking about, we do not reference the position of the cube in the last frame. We're going to change the angle and rebuild the cube's new coordinates from the original with our adjusted angle. So to do this, we're going to take our angle and we're going to add the adjustment to it. And we're going to use the frame that we captured earlier. I named it frame, but it's really the time value. So what this does, it looks a little complicated, but the gist of it is it's talking about how much of 360 degrees we're going to rotate. I said 0.2, so a fifth of a circle per second, a fifth of a full 360 degree circle rotation every second. And the frame value that we got earlier was out of 1,000 per second, so we're going to divide that by 1,000. And lastly, we don't want our angle to be anything other than within the range of 0 to 360, so we take that value, the new value, and we modulo it by 360 to keep it within a legitimate bound for our use case here. And then that's the end of the main loop. So the only way it will break is if we quit the program with the X button. And if we do that, it will break out of the loop. And then we will hit pygame quit, so it will close the screen. And then we will use sys.exit to exit our program. And we'll be done there. But that was just the main function. And we have to call main, so we do it here. And that's the entire program explained. And now time to see it in action. Thank you for watching. I hope you got something out of it if you stayed this long. And I'll be making a few more videos in the future. Bye-bye. Hey, so I noticed when I was editing this that I missed a few things, so I'm just going to go back and fix them up real quick. I'll go ahead and link where I got the rotation matrices from real quick. And then earlier I had forgot what screen.blit was doing. So to be clear, pygame.display.update, what that does is that updates the screen. But the confusion here was I have a separate variable for screen and surface, as that's how Pygame separates and handles this. So your screen is your actual screen. And a surface is a surface that you draw onto, so you can prepare a surface and then you could put it onto the screen. So at this point, we had only drawn on the surface. So you see like AA circle, we drew on the surface here, and here for our edges. When we do screen.blit, we are blitzing the surface onto the screen. And so I just wanted to clear that up. And also, this code will be available in my GitHub. It'll be linked below. It'll be under the YouTube videos code repository, but I'll link directly to it so you don't have to search for it. Thank you. Bye-bye.